let's take a look at completing the square to put the functions in vertex form. Let's remind ourselves what vertex form is first. One of my favorite forms. So just remember, it's the one where just by reading it, you can tell what the vertex is. That's very, very useful when we start to graph it. And as you see, there's a little coordinate system that we are going to have to graph. And if you remember, the vertex is given by h comma k in this particular form. So our goal is to get this form into the vertex form. And we do this by completing the square. So I'm going to show you my version. And I know there's a few other ways we can do this, but we'll go with what might be nice for us as we're collecting terms. So let's look at first thing when you complete the square. Let me write this over again, just so I have a little more room. F of x equals 3x squared plus 6x minus 2. So the first thing I want to do is move the constant to the other side. We add 2 to both sides. And I know you can probably mentally do this, but I like to kind of show it while we're explaining it. F of x plus 2, pretty much what happens is the left-hand side is a placeholder. So just kind of keep the terms there as you see them. So constant has been moved to the f of x side. The next thing that's super important when we complete the square is we always want to make sure that the squared term has a coefficient of 1. Right now it has a coefficient of 3. So there's a few ways to get rid of that 3 in a sense. I think that the nicest way would be if I divided every term by 3. So notice I'm looking at this. You're kind of dividing both sides by 3, but in a sense, you're dividing every term by 3. Now, the f of x plus 2 on the left-hand side, since it's a placeholder, you could just divide it by 3, all of it, or you can split it up. It doesn't really matter. So when we do this, the next step, we still have f of x plus 2 all over 3, just holding our terms on the left-hand side. When we simplify the right-hand side, the 3 divided by 3 divides out, so we end up getting an x squared. Then we'll have 6 divided by 3, which is a nice integer. That's 2 and x. So this is the way you want to get the right-hand side to look before you talk about completing the square. And so if you remember, and even if you don't, I'll remind you, when we complete the square, our job is to figure out what to add to this binomial to make it a perfect square trinomial, which means when you factor it, you're supposed to get repeated factors. So the way we do this is we kind of look at the formula. If you remember that the idea is kind of playing with the terms in terms of their generic form. So ax squared plus bx. What we end up doing is we take 1/2 of the coefficient of the linear term, that's half of b, and then we square it. And that is the missing constant that we add on to both sides of the equation. And I'll do that in a second. I'll remind myself I'm going to have to do it here too. So I'll put a little square there to say I am running out of room, but we'll work with it. Okay, so let's kind of go through just really quick. The b term, in our case, b is 2. So just kind of a quick computation on the side. I like to write it out because I may use it again later. Kind of helps with the factoring. So half of 2 ends up being 1. If it ends up being a fraction, don't freak out. You'll just work with the fraction. We'll deal with that as that comes along. So we have half of 2 is 1, and we still square it. And half of 2 squared ends up being 1 squared, and 1 squared ends up being 1. So that is the magic number that we add to both sides of our expressions, or I should say the equation in this sense. So I'll show it. I know we could just fill it in. Maybe I can with a little bit of color coding. let me add a little more room just so that things don't get too scrunched. So I'll move this over a bit. Kind of nice that I can do that. Okay, so remember our goal, we were supposed to figure out what do we add to both sides so that the right-hand side ended up being a perfect square trinomial. So that question mark ends up being that we are adding 1 to both of the sides. So the left-hand side, like I said, there's really nothing you're going to do with it in terms of simplify it, but just kind of keep the terms as is. It's kind of nice if you write things over again, just so that you are clear. Then your eyes don't skip and you don't miss anything. And I will write the right-hand side over again, just so that you guys can see that the goal is looking at this trinomial. It's in a very, very nice form, x squared plus 2x plus 1. It does factor. And you can go through the factoring techniques to get it factored into a repeated factor. So we can do that. Factors of 1 that add up to 2. We do know that we have x times x makes an x squared. Factors of 1 that add up to 2, there's only one factor of 1, in a sense. So we should have x plus 1 times x plus 1. And what's kind of interesting, if you've done enough of these, which I have, so I'll just share the secret now, is that the number you get while you're playing with your completing the square formula ends up always being that number that you're using to factor. So that's really, really convenient, especially when the inside, before you square it, ends up being maybe a little more complicated than an integer. So you could probably say, instead of, you could factor it out using all of the techniques, that's no problem there. But we could take a direct shortcut. Knowing that we have completed the square, we can go straight from x squared plus 2x plus 1 to just x plus 1 squared. And so it's up to you. Sometimes I like to write out the steps if maybe I feel a little more complications happening. Like if I get in the teal highlighted part, maybe I get a fraction, maybe I think about it a little more. But we can essentially get down to the perfect square trinomial. And the reason why it's called a perfect square trinomial is you can kind of see, oh yeah, it factors as a binomial squared. So we are almost good to go on this. If you look back up here about what the vertex form was, the whole idea is to figure out a squared term. So you kind of can see it forming here. The issue is that f of x is on one side. And if you kind of look at our forms, and I'll copy this over just so that you see. We are almost good to go. If we were to now isolate f of x, we will have that vertex form. So that is the next thing I'm going to do. And maybe I'll make a note of it to remind myself if I'm taking notes. Isolate the f of x to get the vertex form. Maybe I'll use an exclamation point because I'm excited. Okay, so pretty much you kind of unwrap things kind of in backwards motion. So the last thing we did when we were playing with the left-hand side is we had added 1 to each side. So what happens is I'm going to now subtract 1 from each side. And I know you could probably do it mentally, but I really like to show it. Less chance I make a mistake. So we see I'm going to have f of x plus 2 over 3 equals x plus 1 squared. And we still have a minus 1. Just kind of wrote it in horizontal form as opposed to vertical form. Okay, and then before I added the 1 to both sides, I believe I divided everything by 3. So I'm going to undo this by multiplying every term by 3. So I can multiply the left-hand side by 3 so that the 3 disappears there or clears out. And now I can multiply each term, or if you want to, you can kind of show it where it's the 3 that's getting multiplied to both of these terms. So what you would end up having, you would have the 3 that gets multiplied to the squared term, and the 3 that gets multiplied to the constant. So you don't have to distribute inside the parentheses because the x plus 1 part is bounded by that exponent of 2. It's really just you're giving it to the outside. So maybe I should color code that for you so you see. 3 times 1 is just a 3, and we're just keeping the sign. So now when we look at the left-hand side, we're a little bit cleaner. F of x plus 2. Those 3's, if you kind of are following along, they divide it out. And so the very last step is to subtract the 2 from both sides so that the f of x is isolated. So here we have f of x equals 3 times x plus 1 quantity squared. And minus 3 minus 2 is minus 5. So now what we have is the vertex form. So that would be one part. Maybe they're looking for on the exam. And from that form, and maybe I'll label it just to help us remember, we are in vertex form. From that form, we could identify who the vertex is right away. So if we want to look at the vertex, our vertex is h comma k. So the h is always associated with the x. So when we're looking at the squared term, the vertex would be, it's the opposite of what you see because there's, remember about the horizontal shifting? Same rules apply. So we have -1. And then vertical shifting, it's exactly what you see. So the vertex is -1, -5. So that's probably another thing that the directions are looking for. And I feel pretty accomplished at this moment, but I want to make sure, did we answer everything the question wanted? So we go through and we're saying, okay, complete the square to put the function into vertex form. Cool, we did it. Then find the vertex, check. Now we need to find the y-intercept. So if we want to find the y-intercept, you can do it in a few different ways. I'll color code just a little bit. We'll go here. Let's talk about y-intercept. Sometimes I like to look at the general form. It's a little nicer. If you remember what y-intercept means, it means the y value when x is equal to 0. In other words, where do you cross the y-axis? So we would let x equal 0. And you could do it in either form, but like I said, I like my form. General, because it's a little quicker to compute. So our general form was f of x equals, I'm going to scroll back up just so I can see it, 3x squared plus 6x minus 2. And when x is 0, you're really plugging in 0 to the function. So you're calculating the function of f of 0 or function evaluated at 0. And you may not have to show that you're plugging in 0. You'll probably realize really quickly what happens is that the terms that have x in it end up being zeros. So we end up getting f of 0 equals -2. So that's telling us, if you want to talk about ordered pairs, a little function notation to remind ourselves, we have an ordered pair when x is 0, y is -2. And there's our y-intercept. I know we already labeled it, but I like to label it again. So I'm going to look back down or up. Did I answer everything? Okay, find the vertex, check. Find the y-intercept, check. Graph the function. Okay, so now one last thing. We're going to use our important parts to help us out a bit. And I'll kind of show you a shortcut and you can kind of feel free to do what you like. I always like to plot the vertex first so I can figure out where the shifting has gone. So my vertex is -1, -5. So -1, 1, 2, 3, 4, 5. And we do know behavior of quadratic functions. Even by looking at the general form, we know that the a term was positive. So we do know that it's opening upwards, or sometimes people say smiling. So we have an idea that the vertex is the lowest point of the function, or the minimum. The other thing that might be nice is that when you do plot the vertex, you kind of know what the axis of symmetry is, even though maybe we didn't really address it and it's not asking for it. It just helps us understand that whatever you would plot on one side of the axis of symmetry, then you can automatically find a point on the other side. So I'm going to use the Y-intercept because that's kind of nice. We already took time to figure that out. So it's 0, -2. Right here. And by means of using the axis of symmetry, you can now find the symmetric point on the other side. So that's the cool part. Now this could give you a graph, but usually we want to find a few other points before we draw our graph. It's not quite accurate if you only know 3 points of a parabola. I'd prefer to find a couple more points just to make sure I have the correct width. So a shortcut you can do if you already know where the axis of symmetry is, which we did figure out by the vertex. If you want to label it, that's okay too. That's the axis of symmetry. And it's a vertical line, so that's why the equation would be x equals, and it always matches the x value of the vertex. That's kind of nice. Okay, so almost there. What you probably want to do is find a couple of other points on the function. And you could kind of see you already have points for when x is -1, when x is 0, or x is -2, excuse me. So it might be interesting to figure out like what happens when x is 1 or 2. And then if you can find a point there, then you can figure out another point on the other side. So there's more than one way to do this. We're not really taking away your TI from you, so you could also plug them into the function and find it. But just in case, sometimes we are stuck without a calculator. We want accuracy. It said graph, so we assume that's accurate. What I'd be looking at is maybe choosing points. I might plug it in like x equals 1. I could plug it into the generic form or general form, or I could plug it into my vertex form, whatever you find easier. In any sense, we're pretty good at plugging in college algebra, so I don't have a problem with using the general form. So f of 1 will be 3 times 1 squared plus 6 times 1 minus 2. Take a little time. 1 squared is 1, so we still have 3 times 1. 6 times 1 is 6 minus 2. So 3 plus 6 minus 2. 9 minus 2 gives us 7. So here we go, another ordered pair, 1, 7. And you can kind of see if you were to plot it, 1, 7, 1, 2, 3, 4, 5, 6, 7. And because it's on the right side of the axis of symmetry, you can count 2 units away and you can find the other point, or symmetric point. And feel free to test it if you wanted to find f of -3. I believe you're going to find 7 again. So this is kind of good enough. If you feel the need for more accuracy, you never know. You could try x equals 2, x equals 4, and so on. But I feel pretty good about this. So the last thing, we have the nice ordered pairs, pretty symmetric as we go. What I'll do for myself is do my best to make a U shape. Remember, it's not V, it's U. So we'll do our best to make a U shape going through these points. And we have now completed our problem.